And this, obviously, today's talk will be related to quantum networking. So without further ado, Tiru, thank you so much for taking your time to come and share your research with us. And the floor is yours.
Thank you, Bamba. Thank you for this invitation. I'm glad to give this talk. So today I'm going to talk about an optimal entanglement distribution for policy for a quantum switch. This work is done in collaboration with Professor Don Tousley from the University of Massachusetts in Amherst. So this talk is going to be based on the work that is presented in this paper. So here is the brief outline of the talk. So first I will give a motivation to the problem, and then I will discuss the details of the system model. After that, I will present some analytical and numerical results. Finally, I will summarize the talk and discuss a future work. So the first question is, what is quantum internet? We all enjoying all the benefits of current internet technology. Now, the quantum internet is an internet technology that will work based on principles of quantum mechanics. Why do we need to build a quantum internet when we have already existing current internet? So the reason is that quantum internet will enhance the performance of current internet technology. For example, it can be used in various new applications, as well as it can improve the performance of the current internet. The quantum internet has applications in cryptography, and it helps us to achieve some good clock synchronization, as well as it will allow us to access a quantum computing cloud with high security. Because of various new applications, we want to build a quantum internet. Now, in quantum internet, the main idea is to distribute entangled states for different users that are connected to a quantum network. For many applications of quantum internet, the main requirement is the entanglement of qubits shared between. Now, what is an entanglement? Entanglement is essentially the existence of a strong correlation between two or multiple qubits. For example, here there are two users A and B, which are shared with a 2-qubit entangled states. Now, if user A manipulates its qubit, then that will have an effect on the qubit stored at the other user. And in a given quantum internet, our goal is to create multiple qubit entangled states that are shared between different users. And for example, we could want to create a n-qubit entangled state that is shared by n users. And these users could be attached to the network at different locations. And we want to create such entanglements at the maximum possible rate and to as many applications as possible. But in order to create an entangled state, we could do that by directly transmitting photons through a fiber optic channel from one user to other user. But the main challenge is that the probability of successfully transmitting photons decreases exponentially with the length of the channel. So this is one challenge that we have in creating entangled states for users which are separated by long distances. Another challenge that we have is the no cloning theorem, which says that we cannot copy quantum information. As a result, we cannot have amplifiers that we have in classical internet that will receive information from one user and amplify it to transfer it to other user. So because of these two challenges, it becomes very difficult to create entangled states. But to overcome this challenge, we have a principle called entanglement swapping, which could be performed at a device called quantum switch. Now I will briefly explain this property. So suppose that there are two users, 1 and 2, and we want to create an entangled state shared between these two users. but the distance between these two users is very high. As a result, we will not be able to directly create an entangled state between these two users by transmitting photons. Now, to overcome this, what we will do, we will place a switch on the path between these two users. First, we will create two primary entanglements, which are shown by green and red color. The first primary entanglement is established between user 1 and switch by directly transmitting photons. And the another primary entanglement will be established between user 2 and the switch. Now the switch will have two qubits. One qubit corresponds to the first primary entanglement and another qubit corresponds to the second primary entanglement. Now the switch performs certain operations on these two qubits, which would result in certain classical information that will be transferred to user 2. User 2 will again perform certain tasks using this classical information, which would result in creating an entangled state that is shared between user 1 and user 2. So by using the entanglement swapping operation at the switch, we are able to create an entangled state that is shared between user 1 and user 2, which who are also separated by long distances. Now, in a given quantum network, we will have several switches and routers that are part of the network, and users will be connected as end nodes to a given network. And essentially, our goal is to use the resources of this network, like properties of switches and capabilities of switches, in order to establish entangled states shared between different users. For example, in this network, we could want to create an entangled state shared between user A and user B. And similarly, we could want to create a 3-qubit entangled state shared between user B, C, and D. And each switch will merge primary entanglements generated across the attached links. Essentially, we need to use capabilities of different switches in order to create end-to-end entanglements for different user pairs. Now, applications will generate requests for end-to-end entanglements. So, given the quantum network would need to serve these requests that are arriving for end-to-end entanglements. Now, how do we solve these requests by exploiting the resources of the quantum network? So, what is the optimal way to generate such end-to-end entanglements to serve different types of requests? So, in this paper, we looked at a single quantum switch, and this switch is connected to different users. For example, we assume that there are k users which are connected to the switch, and user I is connected to the switch using optical fiber link Li. So here user 1 is connected to the switch via link L1. And for our analysis, we assume that the time is discrete. That is, the time is divided into different time slots. Now, across each link Li, in every slot, we will create one primary entanglement with probability pi. And with probability 1 minus pi, we will not have any primary entanglement. So this is the simplest model. And each link level entanglement, that is also called primary entanglement, has decoherence time in such a way that it cannot be used after one time slot. That is, suppose if a primary entanglement is created in time slot L, that primary entanglement must be used in the same time slot to create an end-to-end entanglement. Now, the goal of the switch is to combine different link level entanglements or primary entanglements in order to generate end-to-end entanglements for different users. So, so to the given switch, we will also have requests coming in from different applications for end-to-end entanglement. For example, in this figure, I have shown 3 types of requests. For example, the first type asks for a 2-qubit entanglement said between user 1 and user 2, and the second one asks for a 2-qubit entanglement said between user 2 and user 3. And similarly, the third type asks for a 3-qubit entanglement said between all the three users. For this switch, on the right side, I have users connected to the switch, and the left side, I have requests coming in from different applications. Now, each type of request are served in first come, first served manner. That is, the request that is arriving first will be given the priority. And requests are also arriving according to some IID distribution. And the average number of requests that are arriving in each slot is denoted by lambda. On the left side of this switch, I have different queues. This first row corresponds to the queue of the type 1 request, and the second one corresponds to the queue that will store the request of type 2 request. And these dash line indicates the users that are associated with each type. For example, the type 1 requests are connected to user 1 and user 2, which means that this type 1 request will be served if the switch creates an end-to-end entanglement that is set between user 1 and user 2. So this is the system model of the switch. Now, to serve each type of request, several conditions needs to be met. For example, in order to serve a type I request, there are three conditions that needs to be satisfied. First, the switch must make a decision to serve a type I request. And the second thing is that all the links that are associated with this particular type of request must have primary entanglements. And the third property is that the entanglement swapping operation, that is measurement operation done by a switch, must be successful. So this is also a probabilistic operation, and this third step also must be successful in order to serve a particular type of request. So here is one example. So I assume that in a single slot, two links L1 and L2 have primary entanglements. And this is shown by having red color on these two links to indicate that these two links have primary entanglements in a slot. Now, since there are no primary entanglements on third link, so the switch can only serve type 1 request to create an entanglement between user 1 and user 2. So what it will do, so it will perform a swapping operation, entanglement swapping operation, and that operation will succeed with probability R1, which would result in an end-to-end entanglement set between user 1 and user 2. Now, whenever we create an end-to-end entanglement for these two users, then we will remove one request from this queue. So in this way, requests stored in queues are processed by creating end-to-end entanglements for the requested users. Now, I have another situation where all the links have primary entanglements in a given slot. Now, there is a competition among different types of requests to exploit these primary entanglements for creating end-to-end entanglements. For example, we have three types of requests. Now, all of these three types can be served. So one request for each of these types can be served because every link have primary entanglements. Now, how do you make a decision in selecting a particular type of request for service? And we want to do that by in a manner such that the scheduling policy stabilizes the switch. Here, what I mean that these requests are processed according to some scheduling decision that we make in such a way that these queue sizes of requests are finite over time. That is, their average queue size is finite over time. Suppose if you make bad decisions, then the requests that are coming for end-to-end entanglements could just store in these queues, and the queue size could converge to infinite over time, which indicates that our switch is not able to serve requests coming at these rates. So we want to find a scheduling policy that can stabilize the switch for given rates. So before we describe our work on quantum network, let us take a look at how a switch operates in classical networking. In classical networking, our goal is to transfer packets from input ports to output ports, and the switch has a different number of input and output ports. For example, here on the right side, I have shown three output ports which are numbered as 1, 2, 3. And the left side, I also have three input ports, and at each input port, I have requests coming in which needs to be transferred for different output ports. For example, this queue has requests coming in, has packets that needs to be transferred to the first output port. Similarly, this queue corresponds to the request that needs to be transferred to the second output port. And for example, this last one corresponds to the packets that needs to be transferred to the third output port. And these packets are also processed in the first come first serve manner. And there are two conditions. One is that at every time instant, every slot, from each input port, we can only remove one packet. And another constraint is that every output port can only receive one packet from any one of these input ports. So now the scheduling decisions are defined by a matrix called matching. So this matrix has elements pi ij, where pi ij is either 0 or 1. And um, the fact that each input port can only transfer to only one output port is represented by this condition. That is, the column sum of these elements is 1. And similarly, each output port can receive only from one input port. Also is represented by this condition, which says that the sum of the sum of row elements in a given row is 1. Now, in a given matrix, now if an element pi ij is 1, then the switch will make a decision to transfer one packet from input port I to output port j. So in this way, we can define the scheduling decision for a given switch. Now, how can we solve cleverly these requests so that the switch is stable? For this, I will give a simple example. Suppose I have a single server with which needs to process two types of requests. One type of request is coming at rate lambda, and these requests are stored in this queue, and each of these requests are processed according to first come first service basis. And there is another queue which actually stores another type of request. Now, the best way to solve these requests is that you look at you look at the sizes of queues at both the queues, and then you give you give service to the one which has large queue size. This server has one condition that it can only serve one request per slot. Now it has to make a decision in selecting a request from one of these two queues. Now the optimal way is to select a request from the queue that has maximum size. So in order to minimize the waiting times of requests in getting their service, the server must select a request from the queue that has maximum request. So in this way, we can stabilize the switch. We can stabilize these queues. Now, there is an optimal policy that was designed for a classical switch. So here, in this simple example, we were giving priority to the queue that has maximum queue size. But when now in a classical switch, when you have multiple types of requests to be served in parallel, we want to select a particular collection of requests such that their sum of queue sizes is maximum. So in this policy, which is called max weight policy, we want to select a matching which defines the types of requests that can be selected for service, such a way that the sum of queue sizes of selected requests under the given matching is maximum. So here Qij indicates the queue size of request that for output port J at input port I. The scheduling policy essentially selects a matching that maximizes the sum of queue size of selected requests. So here we are here the switch is giving priority to serve a collection of requests whose sum of queue sizes is maximum over all other choices. So this would help us actually to remove requests from queues in fast manner. So this work was done in this classic paper, which shows that this policy would stabilize the switch for all feasible arrival rates of requests. Now, in this work, we actually developed this type of policy for a quantum switch. Now, for that, first we need to come up with the right notion for matching. So, in this case, matching is a vector pi, where each element pi I is either 0 or 1. And since the primary entanglements have decoherence time of one time slot, and there is only one attempt to create a primary entanglement, so every link can have at most one primary entanglement in each slot. So as a result, the primary entanglement of a link can be used by only one request. Hence, we select a matching pi such that the sum of all the pi i's, which corresponds to link Lj, should be less than or equal to 1. So this summation term indicates the total number of primary entanglements of link Lj that are requested under the matching pi. And since the link Lj can have at most one primary entanglement, so the summation term must be less than or equal to 1. So this defines the matching term. Now the switch chooses to select a type I request for service if pi I is set to 1. Now there will be several number of matchings. Now out of all those possible matchings, we need to cleverly select one matching one matching for service in such a way that our selection process stabilizes the switch. So now, similar to the classical work done in the classical networking, we come up with a max weight policy for a quantum switch. Here also, we want to find a matching pi among many possible choices, which would maximize this summation term. And here, the summation term has queue sizes of different types of requests, where QIN indicates the queue size of type I request at the beginning of slot n, and VIN indicates the wait for type I request. So this VIN has other information of quantum switch. This includes what is the probability that the swapping operation will be successful for type I request. This probability is Ri, and what is the value of pi I that is present in the matching pi. And then the third most condition is that whether all the links that are associated with type I request have primary entanglements or not. So I indicates the indicator function that says that Tjn is equal to 1 for every link that belongs to the type I request. So here Tjn says that link Lj has a primary entanglement if Tjn is equal to 1, otherwise it is 0. So VIN essentially is the weight for type I request, and under this max weight policy, we are selecting a matching pi which maximizes this weighted sum of different types of requests. And using this policy, we were able to show that our switch will be stable. Now suppose if we focus on a single queue, suppose if the server is able to process requests at the rate of mu, and requests are arriving at rate lambda, then in order to stabilize this queue, the necessary condition is that lambda should be strictly less than mu. So this is a key idea, and we develop a similar condition for a quantum switch to be stable. So in our analysis, we are able to capture the behavior of the quantum switch as the evolution of a Markov chain. And then we define a capacity region, which says that the capacity region is the set of arrival rates of different types of requests for which we can find a scheduling policy that that can stabilize the switch. And we also found a necessary condition which says using the following property. Suppose that if the switch is stable, then what will happen what will happen is that the rate at which requests are leaving the queue will also coincide with the rate at which requests are leaving the queue. That is, the arrival rate of request will coincide with the departure rate of request when the switch is stable. So using this key insight that we have in queuing theory, we were able to obtain a necessary condition which is defined as follows. So lambda must be a linear combination of matching pi, where the sum of these coefficients C pi should be strictly less than 1. And here C pi indicates the stationary probability that matching pi is solved in a given time slot. So on the left side, lambda indicates the arrival rate of requests, and the right side of the summation term indicates the departure rate of requests. So pi is the departing matching in a given time slot with probability C pi. So using this property, we were able to obtain a necessary condition. And what we showed that if an arrival rate vector belongs to the capacity region, then our policy would stabilize the switch. So our policy is also throughput optimal, which means that if an arrival rate vector belongs to the capacity region, then the switch will be stable. Also, suppose if there is an arrival rate vector that doesn't belong to the capacity region, then we will not be able to find a scheduling policy that will stabilize the switch. So this is the sufficient condition. And this proof comes from establishing Lyapunov stability of the given Markov chain. Now we look at some numerical results. So we have simulated a quantum switch which has 3 users and 3 types of requests, and the arrival rate for this model is given by this vector. And we assume that the primary entanglements are created across links according to this probability vector P, where the first element of this vector corresponds to the primary entanglement success probability across first link. And similarly, we assume that the entanglement swapping operations are successful with probability vector R, and where the first element corresponds to the success probability for type 1 request. Now in this figure, what I have shown is the evolution of Q star n as a function of n, where Q star n is essentially the empirical average of different types of requests. So at time slot n, we look at the queue size of different types, and then we take the sum of all the queue sizes, and then we divide by 3. And similarly, we also include the expectation of Q star infinity, which is the stationary average value. So this is the empirical average of Q star j over n slots. Now, as you see, the empirical average is constant, is finite. Hello? So the empirical average is finite, and hello, can you see? Can you hear me?
Yes, we can hear you.
Yeah, okay, sorry.
And we can see, yes.
Yeah, so in this figure, we can see that this average value is finite, which means that our switch is stable for these parameters. And now we consider another example where we actually increase the arrival rates. So this lambda value has elements which are higher than the previous rate vector. Now in this case, if you see, the Q star n is monotonically increasing with n, which means that there are some types of requests for which Q size is increasing exponentially with n. So which means that our switch is not stable under these parameters. So the reason is that the requests are coming at higher rate to the switch, and there are not enough primary entanglements in the switch to be able to process them. So as a result, many requests are getting stored in the queue, whose size is increasing over time. So I also considered another parameter gamma, which is the parameter for creating primary entanglements across all the links. So here we see the behavior of average queue size as a function of gamma. Now, when gamma is small, that is when the primary entanglements are created with less probabilities, then requests will not be processed quickly. As a result, the average queue sizes will be very high. And in fact, when gamma is small, the switch is unstable. So the average queue size is very high. Now, as gamma increases, and since there are enough number of primary entanglements to process the request, the average queue size becomes finite. So there is a threshold point 0.75, after which the switch is becoming stable. So now if you look at the case where the switch is stable, that is when gamma is greater than 0.75. As gamma increases, the average queue size is decreasing with gamma. This is expected because as we have more and more primary entanglements, we will be able to process the request at higher rate. Now, to conclude the talk, so in this work, we investigated stability properties of a quantum switch, and we showed how to come up with a scheduling policy that can stabilize the switch for all possible rates. So in the future work, we want to also consider the case where requests are arriving at some stationary process instead of an IID process. And another work is to extend this analysis to a network instead of a single switch. Another type of work is to focus on coming up with a low complexity scheduling algorithm, because under the max bit scheduling policy, in every slot we need to find a matching that maximizes the metric. Now, when we have large number of matchings, it becomes very challenging. So another case is the setup where the primary entanglements can survive for more than one slot. In the current work, we assume that primary entanglements can be used for only one time slot, and we need to extend the work for the case where primary entanglements can survive for more than one slot. So in this case, we will need to analyze two-sided queues, where one set of queues store requests and another set of queues store primary entanglements. Now, how do we make scheduling decisions cleverly to stabilize the switch? Now, in that case, how do we characterize capacity? Yeah, this concludes my talks. Thank you for listening. So I'm happy to answer any questions that you have.
Okay, thank you so much for the presentation. Very enlightening. Indeed, we all know that networking plays a very important role in the distributed computation. So, whether classical or in the quantum, as you alluded to. Does anyone has any questions? You can see the bar. There's a button called Ask a Question, or you can also just type on the chat. Let's see if somebody who wants to be the brave, the first person to go and ask.
Bob Miller asks, do types of requests commute, i.e. is 1, 2, 2 the same as 2, 1?
Yeah. Yes, 1, 2 is same as 2, 1.
I myself have a question, and it may be too open-ended, but could you elaborate a bit on the stability condition for Markov chains?
Okay.
Maybe you can go back on the slide. I don't know which slide.
Yeah, so here, right? So actually, I simplified this condition here for this talk, but so we obtain this condition from contradiction arguments. So suppose if the switch is stable under some policy, then what would happen, right? If the switch is stable, then what happens is that the rate at which requests are coming in should coincide with the rate at which requests are leaving the system. So that is the arrival rate should coincide with the departure rate. And then now if you have the stability of the Markov chain, underlying Markov chain, then we will have some stationary probability distribution for that Markov chain. Now using that Markov chain, we can obtain probability distribution for the case where pi indicates the number of served requests in the slot. So essentially, lambda must be should be written as a linear combination of pi in this manner, and then in order to have positive recurrence of the Markov chain, in order to have the positive recurrence of the Markov chain, the probability that all the queues hit zero, that is every queue becomes empty, should be non-zero. Now if you have that, then the summation of these coefficients should be less than 1, because when there are no requests waiting in the queues, then we will not have any departures. Since the probability of having request waiting in the queue is 0, becomes non-zero when the switch is stable. So the summation of these coefficients should be strictly less than 1 in order to have the stability of the switch under a policy. So this is the necessary condition.
Thank you.
Do we have more questions from the audience? Okay, I think there is another question. So on the chat, it's Bob again. You looked at the stability of switches. What about the stability of the individual queues? If it seems, and then he goes on to say, it seems as one queue gets backed up because of HW error, SW error, or malicious attacks, all other queues in the switch could stall.
So when you say that switch is
maybe I can bring
him.
Yeah, I'll see. I can bring him on stage actually to ask.
Okay.
Okay. Okay. I'm trying to share. Let's see. Maybe I need to go in order to invite him. I'm getting some. Let's see. I don't seem to be able to invite him. It's giving me some limitation. Too many video. This is stream limit. Okay, maybe just try to stop sharing, Tiru, for a second to see if I can invite him.
Okay.
Yeah.
Sure.
And then if it doesn't work, we just have to go through the question on the test. Yeah. So Bob is able to come in, so he can communicate, because there is a lot of tests in the communication.
Okay.
Yeah. Hello, Bob.
You guys got
Please.
Hi, how you doing?
Yeah.
Hi, Bob.
Yeah, my question is, and I know on larger systems this happens as an issue, a weakness of using the max argument queue length algorithm is that if, let's say, a certain queue gets jammed up for some reason, right, it naturally becomes the longest of all the queues. So you're going to keep trying to clear that, and the other queues which might be working properly get stalled because you're busy working on that queue with a problem. That kind of approach has been used. It could be a result of a hardware problem, a software error, or even, like an internet case, malicious attacks, where somebody throws a way to jam up a particular queue. And basically it takes down all the other queues, they all stop. I know the max algorithm probably doesn't take that into account. Have you even considered that? Because that's a real life issue.
Yeah, I mean, to have stability of the switch means that all the queues should be stable. That is, the queue sizes across all the queues should be finite over time. Suppose if there is some attack on some particular queue, and if its number of requests that are getting stored in that queue is increasing towards infinite, then that means that our system is not stable.
All the patients are returned to real
All right, thanks. Just so I bring that up.
all of the stuff year one. They weren't really dealt with something.
I guess I have a related question. Is there like one central server doing this calculation and allocation of resources, or is that distributed as well?
No, yeah, in this setup, it's a centralized model.
Thank you.
I mean, now we are focusing on the centralized models, but once we understand well the centralized model, the next step would be to focus on the distributed models in order to establish a global network.
And do you see this as a potential thing for enabling distributed computation in the NISC era in the next maybe 5 to 10 years? How do you see in terms of timeline in practical implementation of this type of approach?
I mean, I think maybe 10 years should be enough, I guess, because now people are using satellite networks, right? We could establish entanglement using satellites, and recently there has been some work from Cisco and having packet switch based network for small distances. For small distances we could use packet switching based technology, and for long distances we could use entanglement distribution through teleportation, like in this network. And even for long distances, probably we could use satellites. I think it should be possible in 10 years' time to have some type of networks.
Yeah, I think they've had a considerable distance. I can't remember in miles or kilometers, but like in Illinois between Chicago and Argonne Labs.
But
I mean, they're having a lot of. Go ahead. Sorry. Yeah.
So I think the most important question is handling the case where there is a finite recurrence time for qubits. Here we assume only one time start case, but if we are able to analyze a model where each qubit can survive for more than one start, then that would be interesting. That is the most challenging problem in this case.
Anyone else has any point, any comment to do this, especially those of you interested in classical distributed computation stuff, or even cryptography?
Well, this is very exciting stuff. Thank you.
Welcome. Thank you.
Yeah. So I have a question. More thing. What would you recommend in recent upcomers, especially if you are a young grad, coming into this field? Is it something that's is it the right time to get into this type of research? Do you encourage young people?
Yes, yeah. Because I have a classical network. Earlier, I used to work on classical networking, but now I recently switched to this one, and I find it's very exciting.
And how was the switch transitioning? That transitioning, how was that the journey from obviously the classical networking side to quantum side? How was it?
I mean, initially it would take some time, but the key approach that you follow the same, right, and you will follow the same mathematics. So I think it's nice.
And your department, because obviously this quantum, you do because we met actually thanks to one of the physicists from Durham University. How is your interaction between yourself, the computer science department and the physics department side in terms of work alongst this type of work?
So I mean, interaction is establishing discussions with the colleagues with whom you are interested to work, and then we meet regularly in the university. And also, university has some programs for interdepartment collaborations.
Interesting, because this is definitely a interdisciplinary field.
Yeah.
So it's also like one of those things that when you have different experts from different fields trying to understand the language of the other expert and this type, in order to have some sort of communication, effective communication in terms of the collaboration to move things forward. What anyone else want to make any other points?
I guess that maybe this is really jumping too far into the future when the technology is there that maybe these matrices could consist of qubits rather than binary values.
Yeah. So I mean, that matrix contains how many requests you want to solve of each type. So that matrix doesn't contain qubits, but it contains how many of each type of request you want to solve.
Yes.
Do we have any other point to be added? I have some questions, but I forgot. I will ask that directly to Tiru in our offline meeting stuff. Let's do more with the stuff that we are exploiting on the collaboration side. Come on, guys. Especially the grad students on the audience. Anything you want. Are you encouraged to join Tiru into this line of work, which is very important because you need to get the networking correct in order to enable all the other stuff in terms of doing distributed computation, thinking about all this stuff, distributed algorithms and so on.
I think quantum networking is important even for distributed computing, right? Initially, we will have small quantum computers. In order to make a large quantum computer, we would need to connect different small computers so that we can have a joint large quantum computer which can perform complex tasks. So I think quantum networking is an important field.
Yeah, and maybe this will give us, some useful advantage. As this could be the pathway for that to give us some potential computational advantage, within the NISQ era itself, until we get, a fault-tolerant quantum computer. So the networking is important, isn't it? I remember this slogan. Is it from some microsystem? The network is the computer, something like that.
Yeah.
So this is, it's still true in this age. It's true in quantum computation, in the cloud computing era. It's also true in this new era of computation that we are going through. We are starting. I mean.
And I see the potential of having a greater bandwidth of communication between separated quantum computers. That is actually the key problem in classical computing. Like even with a GPU and a CPU, you're spending most of your time moving data around rather than computing.
Okay. Anyone else? Okay, so maybe I will ask a tricky question to Tiru. Okay, there's a question coming in. Yeah. Okay, so it's a little bit. Maybe I can bring. Would you like Antonio? Would you like to come on stage to elaborate more on this? Is that okay, Tiru? If you are inviting on stage?
Yes, yeah.
Yeah. Let's see. Because the question is very wordy. That's fine. Also, you can read it, but maybe you can put it better coming in.
I think that might be related to things like where the players in a game share entangled information, but that's a guess. But please elaborate.
Yeah. Hello, Antonio. Feel free.
Hello, can you hear me?
Yes.
Great. Thank you for this talk. Yes, I came a little bit late, but nowadays I'm trying to study more about non-lethal games like Mermin, Perez Mermin Magic Square, CS HS game, the quantum graph quantum isomorphisms, and in all these games, there is a referee, right? And there are several players, several parties, and the point is that the referee can be convinced about some property because all the players can coordinate between each other with not without communication, and so at the end of the day, the sharing a quantum state could be used to coordinate the strategy, to implement a strategy non reachable classically, in order to convince the referee. Um, I am asking myself if it could be used somehow in order to distribute the queries or some, I don't know. I was thinking, I was asking myself, maybe you have more information about uh, uh, this stuff. Um,
No, I mean, yeah, I never thought about like those stuff.
okay. Anyway,
But maybe
yes.
go ahead.
No. Go ahead, please.
Yeah, no, I was saying sometimes use cases can come in from multiple angles that even the original authors haven't thought about it. So maybe this could be an opportunity. I think Tiru has on his slides there is his email. If you maybe email him, some if you have a paper, for instance, or some reference stuff to look at it, maybe then he will be able to gauge a little bit more to see whether there is a potential thing. Yeah.
So
Looking at it,
one thing. So can referee play as the role of the switch in this model? If that is the case, I think yeah, maybe these ideas could be help.
I just was asking myself, maybe it is not related. I Google for for papers or for works on this direction. I found, for example, a paper in ResearchGate platform called "Quantum Advantage for Distributed Computing Without Communication." I don't know. I will take a look. Maybe we could find something interesting. Anyway, if I find something interesting, if you don't mind, maybe I could send to you an email or something like that.
Yeah, yeah, sure. Yeah, you are
Great.
welcome. Yeah, thank you.
Thank you a lot.
That will be interesting. A use case.
I think there actually
Thank you. Antonio.
is a strong analogy between game strategies and algorithms. So this is definitely worth pursuing.
Yeah, it's always interesting, these type of I saw something pop up before. Is that the old question from Antonio? Okay, so he's saying just okay.
Thank you, Antonio. Very interesting idea.
Okay, so we have I guess we are on the thing on the hour. Tiru, is there anything you want, any final thoughts or comments or any insight you want to share with us about the future of this? Where would you like, this is more of my question, in 5 years time, where would you like to see the state of quantum networking versus what's possible? What do you think will be possible?
I think at least we will be. I think if we are able to understand the centralized quantum network in 5 years' time, I think that should be great. And because we know how we can handle distributed scheduling, say in wireless networks, maybe we can exploit similar algorithms that we have in classical networking to use them to quantum networking. So yeah, if we are able to address issues that we have in centralized quantum networking in 5 years' time, that should be fantastic.
Cool. Okay, so well, I guess there is no more questions. So thank you so much again, Tiru, for coming and sharing this your line of research, which is very important in the grand scheme of things. So thank you so much. And to the rest, this is the first of a few webinars that are coming up. As you can see, I kind of lost practice a bit because we haven't had webinars for some time, for almost 1 year. So yeah, so I hope you enjoyed. The replay of this will be available later on YouTube. And I leave it to Tiru if you want to share the slides as well. I don't know whether he's happy to share them if people email him or something, or you can just maybe send it to me. I will distribute it to the rest. If not, yeah. Thank you so much, and yeah, have a good day. George, you want to say something?
Yes, I mean, if there's a problem with all of the slides, maybe at least the references to papers like McCone and so forth.
Yeah, I mean, I'm happy to share the slides, so I will share the slides after this.
Okay, good. And then I will distribute them to the rest of the audience and the community, especially the ones on Discord. Okay, so thank you so much again for joining us on this Monday. I know Mondays are always slow for everybody, including myself. So, Tiru, thank you again for taking your time, and George, thank you so much for helping, and everyone else on the chat, thank you so much, and I'll see you next time.
See you later. Thank you.
Okay,
Bye.
see you later.